Good afternoon. We are going to start the isogeny track with a couple of minutes of delay. Welcome all for joining here. I'm slightly biased, but I think you made the right choice in coming here. First up, we have Ricardo Invernizzi, who will present Pegasus, which is joint work with D'Artois, Eriksen, Huitzach, Lemerdi, Robert, Ruber-Gouten, and Zolowski. Have at it, Ricardo.
Thanks you for the introduction. Thank you for having me here. And as you mentioned, today I will present how to compute practical and effective class group action from isogenies. So first of all, a natural question is, what is a group action and why are they so interesting? So class group actions are known, or group actions in general are known to provide a quantum secure replacement for DLP. Formally, a group action is a map that we can define from a product. So we take a group G and a set X, and from this product, we define a map into the set X itself. More practically, one may think of every element of the set of the group G defining an operation over the set X, and this operation has to be compatible with the group structure of G. Now, I think there is a very common example that most of you will be familiar with. If the group is the set of the integers and the set is the invertible elements of a finite field Fp, then we can send the pair xg to g to the x. And this action has a lot of place in cryptography, as you probably know. Now, when we're given a group action, we generally ask ourselves two questions. The first is how efficient it is to evaluate this group action. And in the example that I just mentioned, given xg, how efficient it is to compute g star x is how efficient it is to compute x to the g. And we know this is quite efficient. The second question is called the vectorization problem, which is given x and g star x, how hard it is to recover g. And once again, if we think about the previous example, this is given x and x to the g, how hard it is to recover g. And this is exactly the discrete logarithm problem that is assumed to be hard if the attacker does not have a quantum computer. And this is exactly the reason why group actions were introduced in the first place, to replace discrete logarithm-based construction in a quantum secure setting. Now, one of the first examples of group actions or isogeny-based group actions is the scheme C-side, where we act with ideals over supersingular elliptic curves. Now, these actions are represented and can be computed by isogenies. And thanks to the fact that equivalent ideals result in the same curve and that this action is also commutative, we can define a Diffie-Hellman key exchange through this. Now, I will not get too much into the details. The next talk will explain maybe a bit more how the action works and is computed in practice. But what is important for now is that in C-side, we can only act with smooth norm ideals. This gives rise to what is known as a restricted effective group action. So a group action where we can act only with a subset of the element of the group, as opposed to an effective group action where we can act with any element of the group. Now, this leads to a problem if we're interested in constructing signatures or similar construction. So in the past years, a lot of research has focused on trying to solve this issue. The first big step in this direction was made by the scheme C-fish, followed by all the scallop constructions, where C-side is turned into an effective group action thanks to pre-computations. However, these pre-computations are too heavy and they do not scale. So this is viable only for small parameters. The following step is the recent work, Clapoty, where we get a polynomial time framework. However, this is mostly a theoretical construction. It has no practical instantiation, and we will see in a minute why. The first instantiation of this was the scheme Clapoty with the K. However, this also suffered from some efficiency issues. So first of all, let me set some notation. We will work over a base field Fp, where P is a prime of the form F times 2 to the e minus 1. F is a cofactor that we want to be as small as possible for a lot of efficiency reasons. Now, the biggest threat against isogeny-based group action is a sub-exponential quantum attack by Kuperberg. As like many quantum attacks, the concrete complexity of this attack is not entirely clear. So the current estimates ask P to be between 500 and 4,000 bits. So it is of crucial importance that we are able to instantiate our construction at all these security levels, because we don't know what may come. So let's start from the Clapoty framework, which this work builds upon. As I mentioned, this is a framework to construct unrestricted group actions in polynomial time. Now, the way it works is we take an ideal in the class group, and we look for two equivalent ideals, B and C, and two integers U and V that can solve the equation U times the norm of B plus V times the norm of C is equal to 2 to the E, where 2 to the E is less than P, as we saw before. After we got this, we take the two integers U and V, and we require to compute a degree U and a degree V isogeny. And in the end, thanks to a quite technical but still quite efficient step, we can recover the isogeny phi A, so the isogeny corresponding to our starting ideal. Now, I mentioned that this framework as itself is mostly theoretical, and this is for two reasons. First of all, the solvability of the norm equation. The number of expected solution for that equation is roughly 2 to the E over the norm of B times the norm of C. So it is clear that we want those two norms to be as small as possible. However, we can see our starting ideal A as a lattice, and in that case, short equivalent ideals are shortest vectors in the lattice A. So we have the Minkowski bound that tell us how small can we be, and this is roughly square root of P. So the best ideals that we can find will have norm roughly square root of P. And if we plug this back into the equation, then we see that the number of the expected solutions is roughly 1 over 4f, where f is the cofactor, which is already quite low. After this, we still have to compute a degree U and a degree V isogeny. Now, computing isogeny of a given degree from a random curve is conjecturally hard. The only way out of this that we can find is if U can be expressed as a sum of squares, then the isogeny phi U that you see is actually an isogeny of degree U, but in dimension 2, so from a product of elliptic curves. Now, this forces us to work in the last step in dimension 4, which of course has an impact on efficiency, but is still feasible. However, this also requires U and V to be a sum of two squares. And here comes the second problem. The probability that a number is expressible as a sum of two squares is not that high. So we know that a number is a sum of two squares if when we factor it, all the factors that are 3 mod 4 appear with an even exponent. So we have no factors 3 mod 4 with odd exponent. However, we cannot factor numbers for the sizes that we're talking with. So the only thing that we can do is to do trial division up to a certain bound, hope that everything that we found is 1 mod 4, and then hope that what is left over is a prime, because in the case we can factor. It, and we also have to hope that that number that we find is 1 mod 4. If all these conditions are satisfied, then we can express U as a sum of two squares and compute a degree U isogeny. Now, since we want U and V to satisfy this condition at the same time, the probability that this happens for the size we are dealing with is roughly 1 over log P squared, which builds up on what we have before. So in practice, the situation is really not optimal. We're forced to take 2 to the E less than P for efficiency reason, but then the equation we start from barely has a solution. So to give some numbers, we have a 97% failure rate for the biggest set. On top of that, we require U and V to be expressible as a sum of two squares, and this brings the probability down by either 2 to 3 orders of magnitude. So in practice, the success probability of this method as it is basically 0. Luckily, we can solve this problem by using some tricks regarding small degree isogenies. Now, for the setting we're with, so for the specific shape of the prime, we cannot compute isogenies of small degree in the usual way, but luckily there is an algorithm due to Elkis that allow us to do it still efficiently. And this algorithm also has a complexity that is linear in the degree. So we can only do it for small degree isogenies. But as I mentioned, this will be enough to solve all our problems. So the first problem was the solvability of the norm equation. The number of solutions that we expect from the equation is proportional to 2 to the E over the product of the ideals that we get in. But now if we get two ideals, B and C, and we factor out the smooth part of it, we can act with this small part using Elkis isogenies, and then try to solve the norm equation with the remaining part of the ideals. Now, since we took out some factors from the norm equation, these factors will appear as they are in the number of solutions that we expect. So we multiply the number of solutions that we can expect by the number of factors that we can take out. And this is already quite a big difference. However, we still have the second issue, namely that we need the u and v that we can find from the equation to be expressible as a sum of two squares. But again, using Elki's isogenies, we can act with isogenies of given degree as long as the degree is smooth. Now, the problem that forbids a number from being a sum of two squares are, as I said, the factors that are 3 mod 4. But small factors that are 3 mod 4 will be way more likely to appear. So for instance, 3 appears as a factor in 1/3 of all the numbers. And so if we remove those small factors that are 3 mod 4, the probability increases by quite a lot. And we observe heuristically that only by removing 3, 7, and 11, that are the first 3 primes that are 3 mod 4, the probability of expressing a number as a sum of two squares increases by a factor of 3. Now, we're almost good to go in the sense that now most ideals will have a solution, and we'll have a solution that we can find quickly. But some ideals may still fail or take too long to solve, and we don't want that. And so we can use one last trick, which is the re-randomization of bad ideals. So if for one ideal we cannot solve the norm equation, we can look into neighboring ideals. And again, thanks to Elki's isogenies, we can then, if we find a solution, bring it back to our starting ideal by computing one of these smooth isogenies. Now, this brings us to a 0 failure rate, because for a given ideal that we receive, we can act with all the neighboring ideal, and we can act with as many ideals as we need to bring this failure probability to 0. And in practice, this is even more efficient than one can expect, because we are able to detect quite quickly if an ideal is bad or not. So if an ideal is bad, we don't keep looking inside it. We just reject it, move to a neighboring one, and try to solve the norm equation there. So these re-randomization procedures makes our algorithm better both in theory and in practice. So let's get to some numbers. As you can see, all the scallop-based constructions were quite far from fast. We have the best optimized implementation in C++ of Perl scallop. Took 30 seconds at the 500-bit security level. Clapoty with the K did quite a bit better, but still it took 2 seconds in Rust, so optimized implementation, and roughly 200 seconds in Sage. We already see from here that going from a Sage to a Rust implementation got a factor 100 speed up, so we can expect similar result for us. But our implementation in Sage, so not optimized, for the 500 level took 1.5 seconds. So it's faster than all the previous optimized implementation. On top of that, we are also, this is the first time that unrestricted group action was instantiated at all security levels. So we can now also break down timings a bit more. Basically, what we do in our work are 3 big steps. The first is solving the norm equation. So the norm equation that we had at the beginning. The second is act with a small degree isogenies, so Elki's isogenies. And the third step is the recovery of the final isogeny using a 4D isogenies, so the most technical step. And we see that this third step take up most of the time. For instance, at the 500 security level of 1.5 seconds of total running time, 1 second is taken by the 4D isogeny computation. However, this proportion changes a bit the more we scale up. For the 4,000 parameters, the 4D part is still the most expensive, but the Elki's part, so step 2, is quite close. So the bottleneck is still dimension 4, but we see that the Elki's isogeny scales a bit better. To conclude, this is quite recent work. As I said, is the first practical instantiation at all security level of the Clapoty framework. So we expect that there is still a lot of work to do. The first question is, can we get rid of U and B? And this was a big issue, as we saw before, because they impose a lot of constraints. And it turns out that we can. We have a coming soon work called Qt Pegasus, where we remove U and B from the norm equation. So that's already a big step forward, especially because now we don't need Elki's isogenies. So at the 4,000 parameter set, this achieves effectively a 2 times speed up over the algorithm. The next question is, since now if we remove step 2, most of the time, and by most I really mean 90 to 95% of the time is spent doing 4D isogenies, can we optimize that? Now the computation of 4D isogenies is quite standard. So what we can do to optimize this is to try to do less for the isogenies. The number for the isogeny is the exponent that we had in the norm equation. And so one natural question is try to reduce that exponent. We expect a solution, a smaller solution to exist. So roughly 2/3 of E, where the E is the E that we use now. We expect this solution to exist, but we have no way to find it at the moment. And the last question, which would really be a major improvement, is can we get rid of the dimension 4 part? As I said, this is most of the computation. So if we can avoid that by going to dimension 2 or doing something faster, that would really be a drastic improvement. However, for the scheme, how it is constructed now, we really don't see any way in which this is possible. So for that, new ideas are needed. If any of you has an idea, feel free to talk to me. And that's it. Thank you for your attention, and I leave the floor to questions.
We started a bit late, but if somebody has a short question, that is definitely possible. Okay.
Yeah, thanks a lot for the talk. About dimension 4, question 3. In scale-up HD, there's a really similar equation, except the ideals are principal. So this is how we represent the orientation in higher dimension. Is there an intuitive reason why this fails for ideals that are not principal?
Well, the fact is that the orientation from scallop HD is different from here. So the HD requirement in scallop HD is really to represent the orientation. And so you go to higher dimension to actually compute the orientation. Here, the orientation is the Frobenius, so you don't have that requirement. The reason why you go to dimension 4 is to, in the Pegasus case, is really to solve this norm equation that somehow has nothing to do with the orientation. It's really the representation of an ideal. And so you need this higher dimension because, yeah, for the Canny diagram, and in Pegasus because U, so degree U and degree V isogeny, these are in dimension 2. So computing them in dimension 1, and so making the Canny diagram in dimension 2 would mean computing a degree U isogeny from a random elliptic curve. And this, we know it's conjecturally hard. If that is broken, then I think, yeah, I think Pegasus would come back in dimension 2 and be faster than Qt Pegasus. In Qt Pegasus, we have an even more fundamental issue because there you need to have I. So you need to have something that acts as I. And so you need to go up one dimension. So.
Okay, thank you.
Thanks.
All right, let's thank Ricardo again. Next up is Mark Hoban, but I'm not 100% positive about the title of his presentation yet.
Hello. Okay, perfect. Can everyone hear me well? Guess we need some extra money for the sponsors.
Okay, so this is Mark Hoban, who works at INRIA Bordeaux, and he will talk about deterministic algorithms for class group actions.
Thank you, Thomas. Yeah, so I'd like to know how this thing works. Is it this one? Okay, thank you. Yeah, so my talk is about this world of restricted effective class group actions. So contrary to Ricardo's very nice talk, this is the situation in which we're happy as long as we can act by a sufficiently large subset of the class group. So this turns out to be sufficient if you want to do a key exchange. So my main example will be Seaside protocol. So I'll tell you a little bit about how that works, how we can evaluate that in practice, why it's difficult to do that in constant time. And I'll tell you about a new algorithm that you'll hopefully agree has some nice cryptographic properties. So Seaside, compared to other post-quantum key exchanges, the main kind of selling point is that it's non-interactive. So this means it's one of the very few possible direct replacements of Diffie-Hellman. And it turns out to have exceptionally small public keys. What's less nice is that it's relatively slow. And for a large part, this is because of this sub-exponential quantum attack, which forces us to increase the parameters to a reasonable size. So how does it work? It's a key exchange protocol. So it's a method for two parties to establish a common secret over an insecure channel of communication. So what Alice and Bob do is they start by agreeing on some publicly known starting elliptic curve. And they have two elements, secret elements of a certain group that acts on elliptic curves. So that's what they do. They send the result to each other, and then they act on what they got from the other person. And the reason this works, the reason that they get the same thing, is because this group turns out to be a commutative group. Now, if you do this in practice, you don't really see this group. It looks more like a picture like this. But this is called an isogeny graph. The vertices are elliptic curves. The edges are the maps between them. So these maps are also called isogenies. That's why it's called isogeny-based cryptography. And here the blue, red, and green edges correspond to isogenies of degree 3, 5, 7. So the degree is kind of a measure of complexity of an isogeny. So what Alice does when she wants to compute her public key is she started this publicly known starting curve, and then she does a walk. So she does a bunch of 3 isogenies, a bunch of 5 isogenies, a bunch of 7 isogenies, maybe some other small odd degree isogenies. She ends up at some curve. This is her public key. And now the security assumption is that it should be difficult as long as Alice doesn't tell anyone how many steps of each degree she used to find a path in this graph from the starting curve to the public key curve. So what about this group? There's this class group. It turns out to be the class group of this order that's generated by the Frobenius endomorphism. This is probably my most technical slide, by the way. So if you don't understand everything, don't worry too much. I'm assuming that my curves are super singular. That's where the S in Seaside stands for. And that P plus 1 is smooth. So I need lots of small odd divisors in P plus 1. And this guarantees that for each of those divisors, there's always exactly 2 outgoing Li isogeny. Okay, so this turn out to correspond to prime ideals whose product is principal. In other words, trivial in the class group. That's why these isogenies kind of go in different directions in this cycle. And then if you take the union of a bunch of graphs like this, then you get a picture that I showed you. Okay, so let's do an example. This is a prime number for which p plus 1 is indeed smooth. Alice's secret key is something called an exponent vector. So this tells us how many steps of each degree she's going to take. And there can be negative numbers because she can walk in two possible directions in the graph. Same thing for Bob. And now the reason they get the same thing is because acting by consecutive ideals is like adding the exponent vector. So how do you compute these isogeny walks? You have to know how to compute one of these Li isogeny steps. So we have two of them. Let's look at the first one. An isogeny is determined by its kernel. And the kernel of the corresponding Li isogeny turns out to consist exactly of the FP rational Li torsion points. So how can you possibly come up with this kernel? Well, here's an algorithm. We can take random FP rational points. Then we multiply it by this so-called cofactor. And with a reasonable probability, we're going to get a point order Li, which generates the kernel of the isogeny. The isogeny you can compute using something called Velu's formulas. Now, this particular algorithm is not super efficient. And the main problem is that this multiplication in the second step is by a relatively large number. So this is expensive. It's also definitely not constant time, because step 2 and 3 depend on Li. So if you look at the picture, if every color has a different cost, then certainly from the execution time, we can do something about the number of steps of every degree. So what one way to kind of fix this, I guess the most straightforward way is to use something called dummy operation. So here we take the number of steps that we need to do, so let's call it Si, and we add a bunch of extra steps that we don't really need, just to make sure that we always have the same number of Li isogeny. So the last couple of things we don't really use to resolve, you just throw it away. So, well, I guess there's two problems with this. First of all, it's clearly inefficient because we're literally wasting time. Also, this becomes susceptible to something called fault injections. So if you could inject a fault into one of the isogenies, then if the result doesn't change, you know it was in a dummy isogeny. So this also gives you information about the secret key. Another way, which people call dummy-free, is to a similar trick. So you do the first steps that you need, and then you kind of go back and forth for a little while. The reason people say dummy-free is because if you inject a fault into one of the last isogenies, it does change the outcome. I'm not sure if I would call it dummy-free in the sense that we're still doing wasteful stuff, right? We're still doing some computations that we don't need. But at least it's less susceptible to fault injection. So another method is to pre-compute these so-called full order points. So using these points of order product of the Li's, we can always compute actions by binary ideal class. So we could ensure that we always do exactly one Li isogeny for every I. And this looks better because at certainly constant time, we're not wasting anything. We seem to even avoid this issue of expensive random point sampling because we already have the points. Of course, what's possibly less nice is that we've restricted our key space. And we don't really fully avoid the issue of point sampling because, well, if you do a key exchange, you have to do a group action at least twice. So you still need to sample these full order points on the public key curve. So I looked at some papers on this topic on a constant time C side. And the green ones use some approach of wasteful operation, what I would like to call them. The blue ones are also suggest the restricted key space approach. And this talk, I will try to explain a method that does neither of those. So before I do that, I will change the setting a little bit. So this has to do with the oddest of prime numbers, which is the number 2. So we had this factorization of p plus 1. And this turns out to be the norm of the endomorphism Frobenius minus 1. This corresponds to a factorization of the principal ideal generated by pi minus 1 into a bunch of small norm ideals. The things on the right are the ideals we use in the class group action. The other one is kind of strange. There's this 4 here. I don't really like the 4. The reason it's there, if you know about isogeny volcanoes, is because if you look at the graph of F irrational 2 isogenies, there's no horizontal ones of degree 2. Okay, so what this says is that this ideal doesn't decompose into prime ideal. Okay. So one way to fix this is to change the prime. Make sure p plus 1 is divisible by 8 instead of 4. And then the 2 isogeny graph looks very different. We have this kind of trampoline thing where on the top we suddenly have a cycle of 2 isogenies. And this again corresponds to some factorization of an ideal. So now we have this endomorphism pi minus 1 over 2, which really factors into prime ideal. So now we can kind of like take this 2 ideal and put it in the product. And for free, we actually get an extra ideal to use in the class group action. Now this equation is possibly less trivial than you might think. So what this says is apparently if we do an isogeny of every degree, we get back to where we started. Because this is a principal ideal, so it's trivial in the class group. In other words, the action by the exponent vector of only once is trivial. So we can express this using the kernel. So we can take one of these full order points, as we call them. And apparently the quotient doesn't do anything. It corresponds to the endomorphism pi minus 1 over 2. And well, we can do the same thing kind of going the other way. So we have like one isogeny going clockwise and one going counterclockwise. Okay. But now this also means that if we have a non-trivial ideal class, we can evaluate it in 2 ways. We can go either counterclockwise or clockwise. The counterclockwise one we can compute using this point P. The clockwise one we can compute using Q. And now here's the kind of cool thing. This is the main theorem of the paper, even though you might not agree that this deserves the word theorem. If you look at the isogeny going counterclockwise, or okay, the first one I written down here is the other way around. So let's say I take the isogeny phi minus, so it goes clockwise, and I push through the point P. Then this doesn't get annihilated. In particular, it remains a point of full order. Okay, the same if you go the other way with the point Q. Well, why is this true? Because the kernels intersect trivially. So now I can add these points to the codomain, and I'm exactly in the same situation that I started with. So in particular, you can iterate this action to compute the action by any exponent vector. What does it cost? It's 1 Li isogeny for every I. So in particular, this is constant time. And if you write it down in some pseudocodes, it's pretty short. And you get something that looks a lot like something called the Montgomery ladder. Actually, it's pretty much the same thing, except you have isogenies instead of multiplications. And this has a bunch of nice properties. So it's fully deterministic. We have completely avoid this costly random point sampling problem. It's really constant time in the sense that if you assume that there's constant time finite field arithmetic, this really evaluates in the same number of clock cycles every single time. It doesn't use dummy operations. It allows the full key space. And there's no if-then statement. Okay, so this is something else that is possibly interesting for cryptographic purposes. How much time do we have, Thomas? 1 minute? Okay, so I'll quickly mention the kind of general situation. So the reason this works for C-sites is because we have this factorization, right? So factorization of some principal ideal. This could happen in general. So whenever you have an anamorphism that factors into small degree prime ideals, and assuming that, well, it has a trivial intersection with the dual, this algorithm always works. Okay. So in particular, it applies to more general situations, such as the scallop orientation. There's a few caveats. So there's an additional trick that you need because the representation of the orientation is a little bit different, scallop. And it's probably less efficient because, well, we're only allowed to evaluate isogenies whose degree divides the norm of the representing anamorphism. And sometimes you would also like to use other prime ideals. And that means that this is probably more applicable to a scallop variant, which is called Pearl scallop. Okay, maybe one quick self-promotion about some follow-up work. You can do the same thing if you have an anamorphism, which is a composition of a lot of isogenies of smooth degree. And if you increase the number of isogenies, you actually get a discriminant which is arbitrarily large, independent of the size of the base field. So this in particular gives you a C-side variant where this sub-exponential time attack is no longer relevant in the sense that it's weaker than exponential time algorithm. Okay, so that's it.
Okay, maybe time for one very quick question if someone has. Okay.
So thank you for the talk. Any words about efficiency compared to all the green and blue C-side schemes that you were mentioning?
Yeah, so it's at least as efficient as some of them, but so of course we avoid the random point sampling, which actually makes it, I would say, more efficient than most of them. The ones that it's not as efficient as is the ones that use this trick from C-types. It's called the Matryoshka isogenies. So it's another way to use dummy operations where you don't mask with extra isogenies, but you kind of make sure that different Li isogenies, so isogenies for different Li, get the same cost. So using this, you can quickly increase the key space, and it looks like that's more efficient than the algorithm I presented. But of course, it still uses dummy operations. So if you really care about fault injection resistance, possibly this is better.
Okay, let's thank Mark again for the nice talk with the nice text images. The last talk is online, if I'm not mistaken. So it will just be a video. And from what I've heard, there is no interaction possible unless you log into Zoom. And if the speaker is available in Zoom, he will likely or hopefully answer that. If not, you can probably email him and ask questions there. Okay, so this is Sebastian Spindler, who will present more efficient isogeny proofs of knowledge via canonical modular polynomials, which is joint work with Thomas den Hollander, Søren Kleine, Marcio Mula, and Daniel Slama.
So to start, first consider the following scenario where we have two people, say, Veronica, and then there's a secret present plus Veronica, but he knows the secret. Then, being curious, Veronica says, well, don't be a secret, I would like to know. But maybe because it's a secret of another person, or maybe because of bad prior experience, this person says, well, no, I don't really want to tell you the secret. But then Veronica doesn't really have a reason to believe Preston, and so she tells him, well, I don't believe you. And it seems that the two parties have reached us down. But then Preston has this very idea, well, maybe if I can show you a secret, maybe I can prove to you that I actually know. And of course, Veronica might be thinking, well, how would you do that? And luckily for the two of them, there is a nice technique for this, and besides, one put zero knowledge to some knowledge. Before we get into the properties that we want from such uses knowledge, let's just talk about two various applications. The third area was a multi-party proposed, and for in that setting, we are basically used to enable trust the setup and to ensure that the parties behave honestly in multi-party computations. A great example of such cryptography for this is a computation of a supersimilar perfect polynomial history or a secure or the second area was intelligence, and this was strategy transformation. And the most prominent example of this in isogeny-based cryptography is the family of system. So now that we have some applications in mind, let's talk about the properties. There are essentially four properties, and the first one is kind of immediate from the proof of knowledge, which actually proof of knowledge. This is sort of completeness, and it states that if the person knows a secret, then he should be able to convince the wrong of this. The second property goes in opposite direction. It's the for knowledge, and it states that if the person knows a secret, then he should be able to convince the wrong or to deceive if you want. The third property that we want, and this is kind of a motivated our initial scenario, is to say by NP, and it states that in the process of convincing Veronica, she should actually learn anything about the secret that person knows. Finally, the fourth property is as a near what is known as practical in applications, and this is sort of and it just says that person can produce whatever it wants to use to convince Veronica without her input, and then send it to Veronica, and then Veronica can check what the person has used without only this action. The only thing that she has is just an application from person to Veronica. Yeah, I don't know. Okay, with these properties in mind, well, what about the secret? Of course, this knowledge of secret study, right? If I tell you, for example, that
We're not sure.
largest prime number, then understandably not stop this being some kind of study. So, being cryptographers, of course, we want to base our strategic knowledge on some hard problem. And since we're in a session of Isogeny-based cryptography, we want to base this on assertions. For this, we will define one fundamental object of Isogeny-based cryptography, and this is supposed to discuss. To define this, we start with two primes, and the only assumption we make on these primes is that they are equals for the Canonical statement. Then we can define a specific Isogeny graph with an observation P, and it's a connected directed multigraph, which is of course a neutral graph with no system actions. So the vertices of the graph are just K variables of supersingular curves, and these are called to lie in the field of this word. The edges between the J curves correspond to assumptions between the curves, of which the vertices are the J variants, and correspond to a state of opposite rules, which is not important to us in this talk. So now we have to square, and you know that's the metric, so when you will make C5 and the value averages, which of course raises the question of, well, how does the path happen? And one of the path finding in the graph is actually a hard problem if we are able to works. Of course, having a hard problem always depends on the parameters. So, for example, if you parameters such as the graph has two vertices, then you might sort of much define the path of the graph. But of course, there are appropriate choices, and let's just talk about them. What are parameters? So the parameter sizes that define well, the parameter is usually chosen small, so it also common choices that feel free. Sometimes 5% occur in the future, but that's only correct right and beyond that. Not really the other parameters, that's occurred before us. The prime P on the other hand is quite big. So if you want value bits security, then we want it to have approximately 2 value bits. The reason for this is that there is the median middle approach for pathfinding and a more optimized version of this, which has the same asymptotic complexity, which is called the devastated construct. Okay. So now that we have this problem, let's look at our issues. Now, Person says that you're on a well, for these two chambers, they will have to keep them in this graph. And now Veronica has learned from the previous interaction, so she doesn't actually want to know the path, but she demands that that's loose, so we have to show this path. And now Person is about on the brick wall, how do I do that? And this is exactly what we will explore now. For this, we need 1, 1, and 2. And these are still about variable constraint systems. Each variable constraint systems consists of 3 matrices defined by giving fixed path, and they have the same number of rows and columns. And the second component is the correlated factor, which consists of a constant pointer, and some base components that we and these should be followed as a secret launch. And then the statement, but one has to prove if several constraint system is if one takes the matrix A, B, and C and takes the matrix factor product with the vector 1 and the starting matrix, and then as Mark with here takes the component instead of the first two results, then this should equal the third result. So just for free, basically, it's so comparing sizes and efficient running times as even much with launch. So thank you for one. So for the rest of the talk, we will focus on the process of turning our knowledge of a path into a constraint system. And I should mention here that this is not the approach that we followed originally, but this goes back to work on by Lee, who did this with the sort of classical logic polynomial for trying to develop the suit. However, these classical logic polynomials are quite unwieldy, not that as work, but also increase the degree of prime or the prime of itself, basically. And for this reason, we were thinking, well, can we find some polynomial strips and other than classical polynomials? And the answer to that question is yes. But for technical reasons, mainly that the pointer graph is 0 instead of G 0, we have those 55 primes, those 82, 3, 5, 7, and 30. For these 5 primes, we can now list the canonical model polynomials, which are the model polynomials that we're searching for, just once. And for the top, we don't need to memorize this part, but I also to our checkers. So what you see is that we have, on the one hand, a alpha only polynomial, which is the one variable x. And then other than that, we have just one additional term, namely the product x times j, which is what happens if we obvious. So these are quite small polynomials, but of course we have to go very well. You've mentioned that we can use these formulas and things, so we have to explain time. And this is the main thing we work we did in our paper, is to understand how it works, also in the case of characters that are used. Basically, here, as we could use the first E, that's for the cards all that we are considering. We actually from the one to 0 to 9 G1 in our graph. First one is solution from existence, they can list like we find where one is the volume G is in the one selection. And about the volume G we're in, and also to self conversion of to the S, which signals to the polynomial as a part of the volume G, right? And then we do a transform equations.
And S is 12 over S1, but
this is one statement that we do. The other one is a question of whether the solution is right, because we want to, in the end, form this as a constraint system after all. And for this, we have to devise analogous to the classical in something that if you start with this specific generator, then all the things to classical processor, but we cannot even with the name of line cert. Now, the experts in the room are thinking about supersimilar generator must line this whereas this is a standard just the same data as capacity noise. And the incidence is not. It isn't about the supersimilar generator line this where, but that under appropriate choice of points for tickers or supersimilar tickers, all assumptions between can actually also be defined. So in a sense that edges really are controlled by solutions to checkers and assumptions, the fact that all the certainly corresponds to something about assumptions as well. With this understanding of these problems in mind, we can now move to our application. So for each step that we have on our path, we have a chamber from which we start, a chamber from which we end, and some blue F which we call for our edge. And for this, we have this breaking system that we want to replace the constraint system. There's a slight modification that we want to make, and that is to provide two volume polynomials. So what we can do without changing the solution for the system is just to rescale the second equation by a power of the variable f, and then to divide out this coefficient out against. So to give you some definition for the system that we obtain for the constraint system has the following form. So we have three equations, we have three rows of our matrices, and then we have four variables plus this constant one, which we don't account for. So we have this I and square and this shift to j variables as called variables. Now, let's give you some statistics that also talk about the trees or so first of all, let's just in an abstract way compare equations that equals to non-zero entries of our systems. There you can see that both the equations of variables we have truth of about 1/4 in the LHC case, and for non-zero entries is even a bit bigger. The other thing, of course, is that we can apply a system for L larger than 2, which we did in their paper, and to illustrate how this works, how this impacts our equations, let's look at the number of equations. Of course, we're also letting number of variables and zero base. Just as an aside, we mentioned that the standard here basically serves as a kind of normalization, because if you start with a large animal, then to reach the same assumption, we need to take less steps than if you start with a constraint. And the standard really normalizes to each time. So now, if you look at the number of equations, you notice that from L equals 2 to L equals 3, we have a kind of drop down. So from the black to the orange, which is mounted down. And then in the orange, we have a decrease. And then from the orange to the left from left inside, We have another drop down, and then there's another increase. This has changed. So the factor increase from the left to the right is just really the fact that I'll just want this an even number if we take a half prime and an odd number if we solve that equals 2. And just generally an even degree, which is the x degree of our non-polynomial, behaves nice such as a square x that an odd degree. So for this reason, we actually get some Pythagorean theorem. Then jump from 5 to 7 is exponential starting as another small optimization you can do, which actually turns out to be perfect for mobility 7 and 13, which is why we have another gain here instead of a drop or an increase in those operations from 5 to 7. And we'll go into detail about some optimization works here, but if you're interested in the name, those are the complicated. Other than that, though, you can see that in general it seems that the increase in terms of L is not worth it. In a sense that we talked about, as mentioned previously, we have increased concentrations, even though we are not on this. Okay, so all of these discussions were quite abstract, so let's maybe get some more concrete on the elements of benchmarks. For this, we took elements 2 to compare our approach to problem 3, and we looked at proof times, verified times, and proof sizes, both for Aurora and together. And what we found is that proof time, we have about 1/3 of the proof. For verified time, it's about 1/4, and for proof size, it's about 1/8, which is nice. So we have general improvements all around. Now, of course, to close out, there's the question of feature work, and kind of obviously, if we show different model polynomials to prove that attention at all, can use more model polynomials or other ones to obtain smaller coefficient proofs, and maybe to allow for a bigger range of time stop. And the answer to both of these questions is yes, I can actually do that. And 2, that's the model polynomials that we're currently considering. This is the dependent model polynomials and the video model polynomials. But there are also other model polynomials which might be worth looking into. Finally, another question which is interesting is are there other organizations which might be interesting to get as something proof of knowledge? And here I wrote this solid anything other than saying, well, just stay tuned. Hopefully you'll find something interesting in the future. But for now, I hope this taught piqued your interest, and if it did, we can move forward to our notes to find out later, which will of course also be in the survey proceedings soon. Otherwise, you can also find it in the link below. And if there are any questions, I don't know, or any contribution, and thank you for this.